Hello everyone. For today, we're going to talk about Chapter 11, Equilibrium and Elasticity. We're going to answer three physics problems that we got in the University Physics book. So let's get started. For our first problem, a box of negligible mass rests at the left end of a 1.95 meter, 30 kilogram plank. The width of the box is 75 centimeters and sand is to be distributed uniformly throughout it. The center of gravity of the non-uniform plank is 50 centimeters from the right end. What mass of sand should be put into the box so that the plank balances horizontally on a fulcrum placed just below its midpoint? So for this problem, we're going to look for the mass of the sand. So this is the illustration of the problem. So here we have a sand box which has a length of 75 centimeters, and here is the length of the non-uniform plank from the right end, which is 50 centimeters. So this is the free body diagram. This is the free body diagram of the problem. So here, as you can see, this is the this is the half. The fulcrum is in the middle, so this is considered to be the half. And then, since this one has a length of 50 centimeters, we're going to assume that the length from this point up to this point at the middle of the fulcrum is also 50 centimeters. So all in all, this half, the fulcrum, has a length of 100 centimeters. So to get the length of the other side, since this one has the sandbox has a length of 75 centimeters, we're going to divide this into two. So if we're going to divide this into two, the length from this end up to this point is the length divided by 2 of the sandbox, which is 75 centimeters divided by 2. We're going to get 37.5 centimeters. So to get the length of this point up to this point in the fulcrum, we're going to minus, since we already know that this point up to this point has a length of 100 centimeters. So we're going to subtract 100 from the length of this one, which is 37.5. So we're going to get 62.5 centimeters. And all in all, this point up to this point, we have a length of 200 centimeters. So we're going to use the expression of the torque, wherein torque is equal to Rmg, where R is the distance, m is the mass, and g is the acceleration due to gravity. So to calculate the mass of the sand, we're going to use the net moment of forces on system. So we're going to plug in the values that we have. This one is the mass, and g is the acceleration due to gravity, and this is the length of the right end onto the right end of the plank. So we're going to first we're going to remove the cm and make it to m. So yes, we're just going to plug it in, and the net torque is equal to 0. So next is we're going to compute for the mass of the sand. So we're just going to plug it in. So this one's the value earlier, which is 50 cm converted to cm to meters. We have a value of 0.5. So we're just going to plug it in. This one, move it to the other side, since we need to look for m. So yeah, we have an answer of 24 kilograms. So basically, we have the mass of the sand should be 24 kilograms. So for problem number 2, A uniform 6.6 meter long beam weighing 5,180 newtons is hinged to the wall and supported by a thin cable attached 1.8 meters from the free end of the beam. The cable runs between the beam and the wall and makes a 47-degree angle with the beam. What is the tension in the cable when the beam is at an angle of 28 degrees above the horizontal? So for this problem, we need to find for the tension in the cable. So here is the free body diagram that I made for this problem. So sorry if it's kinda if you cannot understand it. So basically, this one is this one's the long beam, which has a 6.6 meter length. So yeah, and then it makes of this one is this one has a length of 1.8 meter. So yeah, this one's the tension and everything. Yeah. So for this problem, we need to solve for the component of weight along the beam, wherein W sub P is the weight component perpendicular to the beam, which the equation would be weight cosine 30, while for the weight along beam, the equation is weight sine 30. And then the next one, we also need to solve for the component of tension along the beam, wherein the tension perpendicular to beam is T sine 47 degrees, and the tension along beam is excuse me, tension T cosine 47 degrees. So for the net torque, since the beam is in equilibrium, net torque is 0. And then the torque about center of the mass of the beam, we're going to use this equation. So basically, I got 3.3 because I divided the length of the beam, which is 6.6, so divided by 2 is 3.3. And then this one is the length, as you can see in the free body diagram. This has a length of 6.6, and this one has a length of 1.8. So if you going to if you're going to subtract it, you'll get 6 meters. And then we're going to substitute the value of this one, since we have a weight of 5,180 newtons. So we plug it into this one, and then we're going to multiply them. So we have a value answer 14,803.83825 newtons per meter minus T. We're going to multiply this one, so we have a value of 4.3881 meters. And then to solve for the tension, we're just going to transpose this on the other side. Transpose this one on the other side, and then divide it both sides with this one. This is gonna be cancelled, and then we have this equation. Then we're going to divide it. We have a value of 3,373 newtons, or 3,400 newtons. For the last problem, two friends are carrying a 200 kilogram crate up a flight of stairs. The crate is 1.25 meters long and 0.5 meters high, and its center of gravity is at its center. The stairs make a 45-degree angle with respect to the floor. The crate also carried a the crate also carried at a 45-degree angle so that its bottom side is parallel to the slope of the stairs. If the force of each person applies is vertical, what is the magnitude of each of these forces? Is it better to be above the stairs or below on the stairs? Sorry, it's a typo. So we need to look for the magnitude of each of these forces, and we need to know which option is better, to be above the stairs or below the stairs. So this one's the figure of the problem. So this one's the 45-degree angle. Since it's parallel, it also has a 45-degree angle. And this one's the length of the person carrying. Oh no, sorry. This is the length of the crate that the person is holding, and this is the length, the width, and this is the height, and this is the weight. So sorry, for the first condition, for the for step 1, we need to know that the first condition for the static equilibrium, net force acting on the system must be 0 when the system is in static equilibrium. And for the second condition, net torque acting on system about the pivot point must be 0 when the system is in static equilibrium. So this is the free body diagram. So since earlier we mentioned that the stairs creates a 45-degree angle. Since it's parallel, it also has a 45-degree angle. And then since at this point, if we divide this one into 2, we get the value of this and this. This one's the gravity. So this one has a length of 0.25, since earlier the height is 0.5 divided by 2 is 0.25. So since it also has a 0.25, this one's 0.25. So to get the value, the length of this from this, we're just going to, since we know that this one from this one is 0.25, we're just going to subtract it from this one. So we're going to get 0.375, and this is the angle, and it is rotating in a counterclockwise direction, so it's gonna be positive. And then for the next step, we're just going to let F sub 1 and F sub 2 be the vertical forces acting on the crate by the bottom and the top persons respectively. So we need to apply Newton's second law to the system of the person and the crate, and then the total vertical force exerted on the crane. So this is the value, this is the equation. So we're going to rewrite the equation for F sub 1. So we're going to have mass times gravity minus F sub 2. And then here the mass is m. Here is the mass is m, and g is the acceleration due to gravity. So from the figure, we have cosine 45 degrees times length over the 0.375, which we got from the free body diagram. So we're just going to look for the value, and we have 0.265. We're just going to plug in the values in the free body diagram that we have drawn. And then so for the next one, we got the length of the width with it, which is 0.265 meters. And then we're going to look for length sub 2. So we're just going to plug the values that we have from the free body diagram, and we're going to get 0.88 meters. And then we need to compute for the t. So, wait, sorry. We're going to take the origin at point A, or the lower left hand corner of the crate. So when the system is in the equilibrium position, the net torque acting on the crate about point A must be 0. So that we have the equation of T sub A is equal to F sub 1 length sub 2 minus mass times gravity times length of the length. So it is 0. So we're going to get the equation for F sub 2, which is this one. Then we're going to plug in the values that we have, and we're going to get an answer of 590 newtons. And then we're going to after that, we're going, since we have the magnitude of force exerted on the top by the top person, which is 590 newtons, we're going to get we're going to substitute it to get the value of F sub 1. So we substitute it, we're going to have a value of 1370 newtons. So therefore, the magnitude of force exerted by the bottom person is 1370 newtons. So from the result that we have, the force exerted by the top person is 590 newtons, while the bottom person is 1370 newtons. So from the result that we have, we can conclude that the above person has exerted less force than the below person. So therefore, it is better to be the one above the stairs. So yeah. Thank you.